everyone. Let's get started. I need to be strictly on time today. Welcome everyone to today's colloquium. It's a pleasure to have Ruobing visiting us. So Ruobing got his PhD in 2013 from Princeton and then was a Hubble Fellow from 2013 to 2016 in UC Berkeley. And after that, he was a Bach Fellow at the University of Arizona. And after that, took up a faculty position at the University of Victoria in Canada. And Ruobing is an expert in planet formation. He's one of the pioneers of observational planet formation, which we'll hear more about. Yeah, let's welcome Ruobing.
Thank you so much. Thanks, Minkai. Yes, so I'll try to tell us a little bit things we've learned about planet formation in the past few years. So we're looking at a real image of a protoplanetary disk around a star called H.R. Tau. The star is about 1 million years old, so very young as far as stars go. Our sun, for example, is 4.6 billion years old. This image is a dust continuum emission map at 1 millimeter wavelength taken by the Atomic Large Millimeter Array ALMA. So here's a scale bar here. So this is half an arc second or 78 U. This is a solar system on the same scale. So the 4 rings represent the orbits of the outer 4 giant planets, so Jupiter, Saturn, Uranus, and Neptune. So this protoplanetary disk is about 3 times the size of the solar system, or the disk goes out to about 100 EU. So what do we see in this image, right? We see a bunch of bright rings and narrow gaps. And they're elliptical. They're elliptical because we think they are circles in the frame of the disk, and they look elliptical because the entire thing is inclined. And also, all those rings and gaps, they're concentric. That indicates everything is in the same plane. There's no 3D projection effect here. So dust emission at this wavelength trace the distribution of millimeter-sized particles. So the bright regions have more dust, and the dark regions have less dust. So this disk, the material distribution is uneven. Some regions have more material than the others. So structures in protoplanetary disks like those rings and gaps have been found in a few hundreds of systems in the past decade, and they represent the most significant advancement in this field, planet formation. This field is very young. This image is actually the first high-resolution image of any protoplanetary disk at this wavelength, and this image was taken just about 10 years ago. Right. So yeah, as mentioned, I will try to highlight some of the things we learned from resolved observations like this. So our main goal is to figure out how do planets form, or more specifically, how to go from here to here. So we know protoplanetary disks are the birthplaces of planet, but we're not entirely sure how that process played out. So the initial condition in protoplanetary disk is the following. The disk is made of gas and dust particles, and the dust particles initially are small. They're micron-sized. Protoplanetary disk inherit those particles from the star-forming environment. And protoplanetary disk only lasts for a few million years. So at the end of a few million years, in most systems, a planetary systems would have already formed. So something needs to happen to go from gas and micron-sized dust to planets within a few million years. So there are 2 ideas how that could have happened. The first idea is called core accretion planet formation model, and this is a bottom-up process. We'll be looking at the size ladder at the center. So our initial condition is, as mentioned, micron-sized dust, and our goal is to form planets in a few million years. So the terrestrial ones are about 10 to the 4 kilometer in size, and the gas giants are 1 order of magnitude larger. So we need to cross this 14 orders of magnitude in size within a few million years. So in core accretion, this whole process is broken into a few steps. For this talk, let's not worry about the details of each step, but let's just say in each step, some physical mechanism works and grow material by a few orders of magnitude in size. And then at the end of that step, the products are passed on to the next step, and then another physical mechanism will take over and continue growing the material by another few order of magnitude. So step by step, it's like a relay, and eventually micron-sized dust and gas are converted into planets. The second idea is called gravitational instability, and this one is a top-down process. So if a protoplanetary disk is massive enough, then the self-gravity in the disk could work and collapse part of the disk itself to form self-bound objects. So here we're looking at a hydrodynamic simulation of a massive disk. So the self-gravity kicks in and excites spiral-shaped structures, and then part of the spiral arms break and fragment to form those red and black self-bound objects. They are the protoplanets. They will continue to evolve in the system to eventually form planets. So we have two ideas, co-accretion and gravitational instability, and in reality it's more like we have two schools of ideas because each of the two has multiple flavors. So how do we know out of all these models and ideas which ones actually work in the real universe, right? To do that, we hope to compare the predictions of these formation models with observed exoplanetary systems. Because as you can imagine, different models will predict different outcomes. For individual planets, they will predict different temperature, different mass, and for a population of planet, they will predict different distribution of centimeter axis, for example. So we know we're aware of the existence of many exoplanets. For example, we have our own solar system, right? A planetary system around a 4.6 billion years old star. So can we use systems as old as the solar system to test planet formation models? You can, but this is going to be very difficult because such systems have evolved for billions of years between their formation and today. Therefore, the properties of those planets have changed. For example, in the solar system, we have 8 planets today, but who knows, maybe we had 10 planets at the beginning and we lost 2 of them sometime in the past 4.6 billion years. And also the luminosity and the temperature of the systems of the planets in the solar system have definitely changed as well. So to make connections between an old system like the solar system to planet formation models, we need to know how the system have evolved, and that is generally really difficult. To test planet formation model, ideally we hope to find planets that are still forming in disks. These planets can directly provide fundamental properties or parameters in planet formation, such as the location, the time scale, and the local environment in planet formation. But unfortunately, directly finding planets in protoplanetary disks is very difficult. So here we're looking at planet mass versus age for a bunch of detected exoplanets. A few thousands of exoplanets have been found to date, and this is a subsample of that. So in terms of horizontal axis, this is 1 million years, then 10, 100, a billion years, and then 10 billion years. So if we put solar system here, solar system is 4.6 billion years. H tau is 1 million years, and this shaded region marks the planet formation timescale. Clearly, most discovered exoplanets are around here. So to the zeroth order, they're all like the solar system. They're orbiting around billion years old star. Without going to the details, let's just say this is caused by the fact that the two most prolific planet detection techniques, radio velocity and transit surveys, works the best for old stars. They don't work well for young stars, which is why there are very few planets located at this within a few million years around stars with a protoplanet. You may say, okay, there are a few guys out here. It's true, a few planets have been discovered, but they're really massive. You know, they're on the order of 10 Jupiter mass. They're probably the outliers of planet formation, and they tell us something, but that's not the general outcome. So we need planets here, but we can only find planets here. So what do we do, right? So to overcome this difficulty, an indirect technique to infer the presence of planets in disks have been developed in the past 10, 20 years. And this is by looking for the structures produced by planets in disks. So the idea is very simple. Planets are gravitational perturbers. So in disks, they can perturb the material distribution and produce structures. We call this process gravitational disk-planet interaction. So here we're going to look at a movie that will give us a basic idea of how this process looks like. So this movie is from a hydrodynamic simulation and will show how the disk responds to the presence of a one Jupiter mass planet right here. We're looking at surface density of the disk. Initially, the disk is smooth, and we'll be in a frame co-rotating with a planet, so it won't move. So let's drop the planet very quickly. It launches spiral-shaped structures in both the inner and outer disk. They're actually density waves. And then the planet removes material from its corporeal region to open a gap, an annulus low-density region. And then the gap edge forms a large-scale asymmetric structure that also goes around the star. Now, the planet itself is very small and faint next to the bright star and the big disk. So it is difficult to see. But these planet-induced structures, these spirals, these gaps and symmetries, they are a lot more prominent than the planet itself. If we can directly see these structures in resolved images of disks and convince ourselves they are produced by the embedded planets that are difficult to see, then these structures can be the signpost of planet. So that's a basic idea. So this is similar to how we find planes in the sky sometimes. So here in this picture, you know there is a plane, even if you cannot directly see it, because the plane leaves behind a tail. So in protoplanetary disk, these structures induced by disk-planet interaction are the tails left behind by the plane. They can also help us infer the presence of the planet and actually constrain their properties. So this sounds straightforward. You may say all you need to do is to go out and take a bunch of images of disks and look for these structures. However, even that is not easy to do, and the kind of observations that are capable of doing that have only been enabled in the past sort of 10, 15 years. To see why that is the case, let's ask a zeroth order question. What kind of observations are we talking about if we want to look for such structures in a real disk? We can address this question from back of the envelope order of magnitude estimate. So we know protoplanetary disks are located in star-forming regions, and the nearby ones are at a distance about 140 parsec away from us. The location of planet formation, we don't exactly know where planets form, but let's use the solar system as a reference. So the outermost planets in the solar system, Neptune, is at 30 AU from the star. So let's just say 30 AU is a characteristic scale of planet formation. And then next, the size of planet-induced structures, such as the width of the gap, is typically a fraction of the planet's semi-major axis. So for a planet at 30 AU, we're talking about a few to 10 AU. And finally, 1 AU at 140 parsec will subtend an angle about 7 millisecond, or 4 times 10 to the minus 8 radians, a very small angle. So if you put all this together, you see in order to detect these structures in a nearby protoplanetary disk on solar system scale, you need to satisfy two conditions. First, you need an inner working angle no bigger than 30 AU, or 0.2 arcsecond. This is to say you need to be sensitive to what's going on close to the star. And also you need angular resolution, a few tens of milliarcsecond. This is needed because you want to spatially resolve all these structures. This resolution is very high. It's about the resolution you need to recognize a coin if you put it in Gaussian and try to look at it from here. Regarding the first condition, this is similar to how we can find a firefly next to a bright lighthouse. You need to somehow turn off the lighthouse in order to see the faint fireflies. So in disk observations, you need to suppress the light from the star in order to see the faint structure in the disk next to the star. This is, of course, only needed if you're working at optical and infrared wavelengths in which the star is a lot brighter than the disk. So as mentioned, observations satisfying these two conditions have only been sort of robustly developed in the past 10, 15 years. So in the next two slides, I'm going to show you two examples of observations at two wavelengths, and I'm going to compare an old observation with today's observation to see what has changed. So here you're looking at two images of the same disk, TW Hydra, at the same wavelengths, H bands of 1.6 micron, and on the same scale. This is 50 AU in both images. This one is taken by the Hubble Space Telescope HST in 2005, and this one is taken by an instrument called SPHERE on VLT 10 years later. So at this wavelength, near infrared, we're looking at scatter light, so dust particles so starlight being scattered by small dust particles in the disk. So in this image, we see a gap at about 80 AU from the star, so it's an annulus region with less intensity than the surrounding. So the primary difficulty in imaging disks and near-infrared wavelengths is how do you suppress light from the central star, which is very bright. So HST does so by putting this funny-shaped coronagraph, this is a physical object, in front of the star to block its light. Because of this, the inner 50 AU or so is not accessible to Hubble in this case. This is called an inner working angle, and this inner working angle is reduced by a factor of 10 in this image. So here in this VLT SPHERE image, we can see the gap at 80 AU with better signal noise ratio, and we can also see a second gap at 20 AU, so Uranus orbit, that is not accessible to Hubble here. So what has changed? As it turned out, I mean, it's same disk, same wavelengths, same scale, but this one is a total intensity image, but this one is a polarized intensity image. So HST records every single photon reached the telescope, but this one, in the image, we only see linearly polarized light. And the reason to take polarized light images is simple. So direct starlight is not polarized, but scatter light from the disk is highly polarized. So if you take two images of the disk at two different polarization angle and you subtract the two, you almost 100% cancel out the direct contribution from the star, but you retain some signal from the disk. This is why a small inner working angle and a higher signal noise ratio were achieved in this polarized image. Here's another example at a wavelength 1,000 times longer. Again, you're looking at two images of the same disk called MWC758, and at the same wavelength, so around 1 millimeter continuum, and the same scale. This is 50 AU. So this one was taken by the sub-millimeter array, SMA, in 2008. And this one is taken by the ALMA interferometer 10 years later. So at this wavelength, we're looking at a distribution of millimeter-sized particles. So the angular resolution in these observations, they are radio interferometric observations. The angular resolution is marked by the beam size, which is indicated here and here. So in this observation, the whole disk is resolved by two resolution elements. So the resolution is not ideal. Because of this, we cannot see structure clearly. We can see there's some asymmetry. The northern disk is brighter than the southern part, but not much. In the right panel, the beam size or the angular resolution is improved by an order of magnitude. So all of a sudden, this is as if we had a good pair of glasses. So we can see the structure a lot better now. We can see a cavity, some rings on the outside, and then two emission clump. All these structures were here. It's just we cannot see them due to the resolution. And we're fortunate to have this improvement because the ALMA interferometer has a baseline and over an order of magnitude longer than the ASIAA, which resulted in the much smaller beam size here. All right, so here are more images similar to the two examples. All these blue panels are scatter light image at around 1 micron, and all these are ALMA observations at millimeter wavelengths. And similar images have been taken for a couple of hundred disks. So the takeaway is in most of them, we see structures. The disk is not smooth. The most common ones are rings and gaps, like these guys. We also see spar arms, like these ones, also this one. And then there are disks with some other type of asymmetric structures and also cavities. So the central question behind all this image is what create all the structures? And for those of us who care about planet formation, are these structures produced by planets? If they are, then we can perhaps infer the presence of planets, constrain their properties, and use these planets to test planet formation models. So to address that question, we have to compare observed structures with what we think planet-induced structures should look like. And if the two agree with each other, we can say at least the observed ones are possibly produced by planets. So a planet can produce roughly 3 types of signatures of structures. There are density structures in terms of how material is distributed, which we have already seen in the previous simulation. And there are also kinematic signatures in terms of how gas moves in the disk, as well as temperature signatures. So in the next few slides, I'm going to talk about each one of them and compare data with simulations. So first, density signatures. So here you're looking at 2 images of the same disk, MWC75A, on the same scale. This is 50 AU in both images, but at 2 different wavelengths. This one is a near-infrared, so 1 micron scatter light image, and this one is the ALMA image at a wavelength 1,000 times longer. So in this image, we see a pair of grand design arms at a few tens of AU in a near symmetric configuration. And this one we see the cavity, the rings, and the emission clumps. Here you may wonder why these 2 images of the same disk look so different. The zeroth order answer is these observations, they probe the distribution of dust particles of different sizes. So in this one, we're sensitive to the distribution of micron-sized dust, and this one we're looking at millimeter-sized dust. So the 2 images look different just because mostly the dust particles have different distributions for particles with different sizes. So all these structures can be explained using 2 planets in the system. So here at the bottom, you're looking at synthetic observations of disk-planet interaction models. So they represent how we think planet-induced structures should look like in observations. They're produced from a hydrodynamic and radial transfer simulation. So this is a synthetic scatter light image of a model, and in the model, a multi-Jupiter mass planet is placed on the outside at around 100 AU. And such a giant planet can drive a pair of grand designed arms inside its orbit, similar to the observed arms. And the same planet can open a gap. This is a synthetic millimeter observation, and forms a dust ring at the gap edge. And then the dust ring can become unstable. The technical term is called Ruobing instability. The instability can produce a vortex in a disk. A vortex is like a tornado, and it sucks millimeter-sized particles to its center. And because in millimeter continuum observations, we're tracing the distribution of millimeter-sized particles, a vortex will look like a millimeter emission clump. And then a second planet, also Jupiter mass, is invoked in the inner disk at 35 AU. This one also opens a gap, forms a ring on the outside, and then triggers formation of another vortex. So together with these 2 planets, we can explain qualitatively the main features, the spirals, the cavity, the rings, and the emission clumps. All right, kinematic signatures, how gas moves in the system. So here's a schematic of an accretion disk. So here's a star. And if there's no other source of gravity in the system, what does the gas do? Well, the gas will just be doing a simple Keplerian rotation around the star, right? So gas will just be going around the star on Keplerian orbit. Very simple, nothing else. But if there are other gravitational sources in the system, for example, if there's a planet which acts as a gravitational perturber, the gas in the disk will be perturbed, and they will develop motions that are not Keplerian around the star. The simplest type of such non-Keplerian motion we can think of may just be a small disk around the planet itself. So in this little disk, the gas goes around the planet instead of the star, right? Just like the moon goes around us. And then the planet can drive spiral density waves, and when gas crosses those density waves, their motion can be perturbed as well. There are other type of non-Keplerian motion in the disk. For the sake of time, I won't go into the detail. But the zeroth order point is, you can use molecular line observations to probe how gas moves in a disk. If all you see is the blue Keplerian motion, you walk away with a conclusion the disk is consistent with no gravitational perturbation. But if in addition to the blue motion will always be there, but if in addition to that you see those one of those red motions, you conclude there are gravitational perturbation in the system. And what that is, it could one of the possibility could be a planet. So here is a real example of a detection of a non-Keplerian motion in the disk and the possible interpretation of planets. These panels are a bit technical for people not familiar with molecular gas observations, but don't worry, for our purpose, the essence behind it is simple. So all these panels are called channel maps. So in channel maps, we're looking at the distribution of gas in a disk that is moving at a particular line of sight velocity. For example, this is a channel map from CO, so carbon monoxide observation, in a disk around a star called HD 163296. So the star is here at 0, 0. And this channel map is at 1.2 kilometer per second. This is the line of sight velocity. And where the emission is where gas that is moving at this particular line of sight velocity. There are, of course, gas everywhere around the star. We don't see the other gas because they are not moving at this particular line of sight velocity. So in this channel map, the emission is sort of in a butterfly pattern. That's a term people use, a butterfly pattern. So the southern branch of the emission is smooth, but the northern branch is not as smooth. There is a little break here. This is a very subtle effect. So the middle panel here shows a zoom in of this local region. Now the black dashed line shows the expected location of the emission if the gas is only doing Keplerian rotation. As you can imagine, Keplerian motion is a motion that you can describe 100% analytical, right? So you can predict where the gas emission should be located at any particular velocity if there's only Keplerian motion. And that's a black curve. The white curve shows the actual location of the emission. So this is the isovelocity contour. Without going into any detail, we can see the white curves disagree with the black curve. And the black curve represents Keplerian motion. That means the real disk in this region is not doing Keplerian motion. That's as simple as that. So why the gas is not doing Keplerian motion? One of the explanation is it is being perturbed by a planet. So the right panel here shows a synthetic channel map. And in this hydrodynamic model, a giant planet is placed at this location, and it is able to reproduce this little zigzag structure in the northern branch of the channel map. All right, the last type of planet-induced signature, temperature signature. So the left panel here shows a gas surface density map of a disk perturbed by a planet right here. And we see those spiral-shaped density waves. Density waves are called density waves because they have higher density than their surroundings. Higher density means higher pressure. So when gas moves into the spirals, they move into a high pressure region, so they're compressed. They're compressed, so they're heated up, they develop a higher temperature. And then when gas leaves the spirals, they go into a low pressure region, so they're decompressed and they cool down. From this simple argument, you can see density perturbation are supposed to come with temperature perturbation as well. And that is realized by the middle panel. So this one shows the temperature perturbation map in the disk. The color bar is arranged such that red is a few Kelvin above the background, so a few Kelvin hotter than the background, and blue is a few Kelvin cooler than the background. The planet is here, and you can see a blue and red shaped, a spiral-shaped blue and red pattern. Those are temperature perturbations associated with density waves. The right panel shows an observed temperature perturbation map in a disk. So using molecular line observations, sometimes we can infer the temperature in the disk. And the color bar is arranged in the same way as the middle panel. So this one, in the real disk, you also see spiral-shaped blue and red pattern in the disk. They may be the temperature perturbation associated with the spirals produced by a planet. All right, so many disks have structures. Simulations show, at least some of them, these structures may be produced by planets. These results represent a good first step, but to use those disk observations to constrain planet formation models, we want to go further. We want to be more quantitative. We need to know quantitative information about those planets, particularly their orbits and their mass, in order to use these planets to test planet formation model, because models make those predictions. So how can we do that? Well, again, the zero-sum order idea is very simple. So if you think a structure is produced by a planet, then it's easy to imagine if you change the property of the planet. For example, if you make the planet more massive, or if you change the planet's orbit, you would expect the morphology of the structure to change accordingly. And if you can find a quantitative correlation between the two, you will be able to infer the property of the planet using the morphology of the structure that you can actually measure in real observation. So one of my graduate students, Shenyuan Mao, run some calculation to visualize this. So we'll be looking at a disk that is perturbed by a planet. This is a surface density map. And as this movie goes, we'll see the mass of the planet increase. So initially, it is about half Jupiter mass. And then we're going to make the planet more massive, and we'll see how the disk evolves. And by the way, this movie here, Shenyuan made it using a neural network. So he is developing machine learning tools for hydrodynamic simulation. He has a website. He's selling his tools. So if you're interested in exploring machine learning, please feel free to check out. So let's start the movie. The planet mass is increasing. You see a bunch of things happen in the disk, right? As the planet becomes more massive, it starts to open a gap. The gap then become deeper and wider, and also the spiral arms becomes more prominent as you know, if you just look at the color, it's getting redder and redder. Now, all these relations can be quantified, and if you can measure, for example, how deep the gap is, or what is the contrast of a spiral arm in a disk, you can use these relations to back out the mass of the planet. And if you do that to a whole bunch of disks with structures, you can infer a population of planets forming in disks. That has actually been done before. For many of these disks, you can apply those relations and get a sample like this. So here we're looking at planet mass versus orbital centimeter axis. So these gray dots are discovered exoplanet, and as we discussed at the beginning, these planets are orbiting sun-like stars. They're a billion years old. These black spots, they are solar system planets. There are 8 of them, and those color symbols are planets inferred from disk observations. They produce gaps, rings, spirals, symmetries, and using the aforementioned techniques, you can infer their mass and their centimeter axis. So where are these planets located? Well, in terms of mass, this is 5 Earth's mass, so super Earth. This is 10 Jupiter mass. And in terms of radius, this is 10 AU and then 100 AU. So right now, the telescopes and instruments that we can use can probe structures produced by planets roughly in this square here. All right, so assuming these structures are produced by planets, there are ways for us to infer the presence of planets as well as to constrain their properties. We can use these planets with quantitative information to test planet formation models. So this sounds really good, but everything builds on a big assumption, right? Assuming disk structures are produced by planets. So far, I haven't shown you any planets themselves. So do we think this is a good assumption? Do we have to use planets to explain structures? This is a fair question to ask. As it turns out, for all types of structures, planets are not the only explanation, and there are alternative physical mechanisms to produce these structures as well. Here I'm showing 3 additional mechanisms that can produce spiral arms in disks that do not involve planets. On the top, you're looking at 3 real images of protoplanetary disks. And the bottom, they are synthetic observations of certain physical mechanisms. So here is a scattered image of a protoplanetary disk around a system called ZCMA. This is actually an ASIAA product here. So this particular disk has we're looking 1-arm spiral, relatively straight on one side. The bottom panel shows a synthetic observation of a flyby event. As it turns out, in star-forming regions, occasionally 2 stars not bound to each other can just pass by each other in close distance. And when that happens, the flyby object can perturb the disk around the primary star and drive those 1-arm spiral, very similar to this. So this is kind of dynamical perturbation similar to planet, but the object is not bound. The middle panel shows an ALMA observation of a disk called Alice 227. This one shows a ring and a pair of grand design arms. The bottom panel shows a synthetic observation of a gravitationally unstable disk. As we know, GI can produce spiral arms, and if the conditions are right, they can produce sort of m = 2 symmetric arms. And this one is a scattered light image of a disk called HD 34282. This one has a couple of rings, and then on this side, there is a little 1-arm spiral, a little hook-shaped structure. The bottom panel shows a synthetic observation in which the disk has a vortex. In inclined disks, a vortex could look like a small 1-arm spiral. All these mechanisms can roughly reproduce the observation, but they don't involve planets. That is not a particularly good idea for those of us who hope to use disk observations to find planets, because now we have a problem, right? How do we know which disk structures are actually produced by planets? We have to correctly identify the ones that are produced by planets. Otherwise, we will be predicting planets that do not exist. So the most straightforward way to address this question is to directly find the planets that are producing the structures. As I argued at the beginning, this is something really difficult, but this is such an important topic, such that on the order of 100 8-10 meter telescope time have been invested to look for planets in disks. And we do have some successful examples. So here is an example showing a disk with gaps and the gap opening planets. So these 3 panels are 3 images of the same disk PDS-70 at 3 different wavelengths. This is a near infrared image. You can see this is inner working angle, and then an inner disk, an outer ring, and then a big gap in between, and then a point source detector here. This is a planet PDS-70b. This middle panel shows a zoom in of the gap region at the wavelengths of H alpha, so optical wavelengths. 2 point sources were detected inside the gap. This one coincided with the planet PDS-70b, and this one was a new detection at the time. And the interpretation is these 2 point sources represent accreting planets. When planets accrete, they can also produce H alpha emission, just like stars. At least that's what we think. And this one is a ALMA millimeter continuum image. Again, you see the inner disk, the outer ring, and then a gap, and then a point source in millimeter that coincide with the H alpha source PDS-70c. So the interpretation is this is dust emission from the circumplanetary disk, so that tiny disk around the planet itself. So observations, we're looking at a gap and then 2 planets inside the gap. And this panel shows a synthetic observation of the system in millimeter emission. So similar to this one, 2 planets are put in to the disk, and they indeed open a big gap from the outer dust ring, just like what we see in the ALMA observation. So this one, again, is a disk with a gap, as well as the gap opening planets. The spiral-producing planets have also been found in certain cases. Again, this is MWC 758. We've seen this image, near infrared, a pair of arms, tens of AU, and then models as a planet on the outside can produce those arms. And then this is a LBT, so large binocular telescope image at 3 to 4 microns, so still infrared, slightly longer wavelengths. You see the 2 spirals, and then a point source here, interpreted as a planet MWC 758c. So this one is at the predicted location in the model. And there are also systems in which both gaps and spirals been found. So this is from Tantan's signature work on AB Auriga. You're looking at dust emission in the color, and then contour shows the gas distribution. So the dust shows a gap similar to PDS-70, and the gas shows a pair of spirals. Tantan predicted the possibility of 2 planets, one here and one here, and now this planet has been found. This is the blue inside here is a Subaru observation detecting a point source here. Now, some of these planet detections are still sort of debated because people are debating whether detections are robust. But the moral of the story is in a very small number of systems, planets have been found and they can produce these structures. But the tricky thing is those examples they're very rare. So for most of these disks with structures, people have tried hard to look for the predicted planet, but in the vast majority of them, they haven't found anything. How do we interpret all this non-detection is not entirely clear. The obvious go-to solution is to argue maybe those planets are too faint, so you're not supposed to see them. That can probably explain some systems, but at least in some systems, the predicted planet, people think they should be detectable, but they're not. And it is pretty much still ongoing investigation in the field. All right, so let's summarize what we have seen so far. So we have seen a whole bunch of disks with structures, rings, gaps, spirals, asymmetries, you name it. And in theory, they can be produced by planets forming in those systems, all the way from super-Earth to super-Jovian mass planet. If that's the case, we can use the observed structures to constrain the properties of those hidden planets that are very difficult to see, and we can use those quantitative information to test planet formation models. This is where we are ultimately going after to figure out how planets form. So, do these models make sense? In some, at least in some systems, they make sense because we found both the planets and the produced structure. But in the vast majority of systems, those planets are still at large. On the other hand, we know there are other mechanisms that can produce structures in disks without planets. So it's not a clear cut. It's not a one-to-one correspondence between structure and planets. So that's where we are right now. So what's going to happen next? There are a few active directions that are being explored in the community right now. I'll just give 2 examples that my group has been exploring sort of lately in the past couple of years. One is we try to present indirect test of the planet hypothesis, and also we're trying to use James Webb to search for planets in disks. So the indirect test idea is very simple. Those planets are very difficult to be directly imaged. So we have to find other ways to test whether they exist. And one of them is to look for the structures produced by planets in other wavelengths. So planet predictions are often made using observations at a single wavelength. But if those planets are there, you can predict structures in other observations. And by looking for those structures, you can form an opinion whether these predicted planets are real or not. Here I'll just give a example to explain this sort of abstract concept. So we've seen this before. This shows a non-Keplerian gas motion and their interpretation as being planet-induced. This is not the only case. There are a whole bunch of other systems. Here every panel is a channel map, and in all of them, non-Keplerian motion has been detected, circled out by the white circle, and the blue dot indicate the predicted planets. These planets are all giant planets. They're multi-Jupiter mass. If they're really there, you expect them to open gaps and drive spirals. So you can look for these gaps and spirals, and if you don't find them, that means something is not working here, right? So my student Jessica Speedy, my other graduate student, decided to look into this. So she took the information about the predicted giant planet in those kinematic signature systems and put that planet into her simulations and produced synthetic continuum emission maps. So here is a planet. It indeed opens a gap in the simulation and drive the spiral arms. The gap is prominent. The spirals are a little less prominent. You can make it more prominent by subtracting the axisymmetric background to produce a residual map. This image now shows the signal to noise ratio of the spiral detection, and the noise is set using a few hours of integration on ALMA. So those kinematic planets can produce spirals that are detectable up to a signal noise ratio of 15 with a reasonable ALMA program on the order of 10 hours. So they're detectable. Therefore, you can go out and look for them. So here is one of her tests. So here's a system called DOAR25, shows this signature little break in the channel map, and then the predicted planet on a circular orbit. The middle panel shows the millimeter continuum emission map. The planet is indeed sitting in a gap, that's good, but we don't quite see spiral here. You can make a residual map by subtracting the axisymmetric component out. Here's a residual map. It looks like the entire disk is axisymmetric, so there's almost no coherent pattern in the residual map. If the planet is there, you expect to see the gap and the spirals. In reality, you only see the gap but not the spirals. What's going on? Again, not entirely clear. It could either be something we don't yet understand about disk-planet interaction, or maybe the non-Keplerian feature can have other interpretations. And finally, as I mentioned, on the order of 100 8-meter telescope time, ground-based 8-meter telescope time have been invested to look for planet. Very few have been found. Now we have James Webb, so people are renewing the search using the new instrument. So in the current cycle, there are 2 GTO programs, so guaranteed time of the instrument team that are devoted to look for planets in protoplanetary disks. So between the 2 programs, 6 objects are covered. You see many familiar names: MWC 758, HR Tau, TW Hydra, and PDS-70. They are some of the most famous protoplanetary disks, and they're famous because they host planet or possibly planet-induced structures. So the goal of these 2 James Webb GTO program is to search for the predicted planet. So both programs are still ongoing, so I don't have a whole lot to show you. I'll just give one example here. The iconic HR Tau system, this is where the entire business gets started. So this is work done by my other graduate student, Cameron Moline. So this is ALMA observation of the HR Tau disk, the first high-resolution millimeter image of any disk. You see all these rings and gaps, and their hypotheses are opened by planets. And now this is a James Webb near-infrared image of the system. Here's the inner working angle. As it turns out, HR Tau is still very young. It's about 1 million years old, so it's still partially embedded in its birth envelope. Because of that, we see prominent envelope feature, as well as a cavity opened by outflow. All these structures significantly affect our ability to look for planet in this region. So here is a detection limit in terms of planet mass as a function of angular resolution. These different curves are results from James Webb observations with different near-infrared filters. They're all sort of similar. The idea is, if there are planets above the curves, James Webb can see it, but if the planets are below the curves, James Webb cannot see it. So toward the outer edge of the detector, about 4 arcsecond or 500-600 AU, James Webb can go down to below 1 Jupiter mass, sort of sub-Jupiter mass planet will be bright enough to be detectable. But as you move inward, as you're getting close to the center, you get larger and larger envelope emission, and your ability to detect a planet deteriorates. These vertical stripes indicates the location of the ALMA gaps. That's where the planets are predicted, and the predicted planet mass are around around Saturn mass. They're here. But in this regime, James Webb can only detect brown dwarf above 10 Jupiter mass. So there's a huge gap between what we need and the reality. So observations like this would potentially explain some non-detection of planets in disks. So the planets are just too faint to be visible with current instrument. But again, we think that's not the entire story, and there's still a lot more to be done with those predicted planets. And with that, I'll stop and take questions. Thank you very much.
Thank you, Robin. We got a couple of minutes for questions.
Is there a certain wavelength at which this stellar environment is less cluttered?
Of course, of course.
Do you expect to see more of the
Yeah, of course. For example, in ALMA observation at millimeter, you don't see the envelope.
You also don't see the planet.
That's right. You also don't see the planet. So you could. So these James Webb observations are between 1 to 5 micron. You could go to slightly longer wavelengths, like 10, 20. They're still covered by James Webb. But the problem there is the angular resolution also get worse. So these guys are very close to the center. So once the angular resolution is getting worse, it's also difficult to detect them. So
So a bigger telescope?
sure, James Webb for planet detection is still a little small for us. It's only 6.5 meters.
So what scope is there for the structures being produced by multiple planets rather than a single planet?
Right.
Could you explain the same observations with two smaller things, which would be harder to detect directly, rather than having one bigger thing which you don't see where you expect to see it?
Yeah, that's a very good question. So certainly there will be systems with multiple small planets. I don't show a lot in this talk because when that happens, the interpretation of the features become somewhat ambiguous because you can present multiple scenarios to explain the structure. If there's only one big guy and produce a characteristic set of structures, those are the easy ones. There's only like one unique solution you can present. So there's other situations also exist, but not too many people look into that. Yeah.
Other questions?
For MWC 758, the planet that's located at 100 AU,
Mhm.
how large do you think the disk actually is then?
The dust disk ends inside that. The gas disk, depending on which molecular species you're looking at, it ends roughly like between 100 to 150 years. So 100 is sort of at the edge of the outer disk. Yeah.
But you need dust to make a planet, right? So you should presume to have dust in the outer parts of it.
Yes, you need dust. You need dust when the planet was forming and at the location of the planet formation. So for that particular planet, first it's unclear how long it has been there, and also it's unclear whether it formed locally.
Okay, and I guess another follow-up question. So these future observations with NGBLA and SKA can observe centimeter-sized grains. So if you look at NWC 758, those with that wavelength, would you assume similar morphology to 1 millimeter, or would you assume different?
If you're going to observe a centimeter wavelength, the dust distribution would yet be different from the ALMA. There are actually VOA observation of that system, and the distribution is already different from the ALMA. Yeah.
Okay, unless you have any urgent questions, I will close the session there. Robin will be here the rest of the day and possibly tomorrow morning,
Yeah.
I guess. So please feel free to find him, and there will be another platform talk in about 7 minutes next door. Catch that as well. With that, let's thank Robin again.
Thank you.